Okay, so welcome back. So let's just start with an overview of our previous strategy of how we've been doing things. So strategy of trying to understand unknown parameters in a population of interest. Let's actually just start with an example. Say we have some Bernoulli population with some unknown parameter theta, and we're trying to figure out about what this parameter is. So we think of this parameter theta as the probability of success. So Bernoulli population means that each sample is like a coin toss. It's a yes or no, 0 or 1. And we're trying to figure out the probability of getting a success. Okay, so what do we do? Let's say we do, for example, 7 trials, 7 coin tosses, so to speak, and we get 6 successes and 1 fail. So first, if this was a different kind of course, if this was a different kind of question, we might ask, what's the probability that our parameter theta is at least a half? And, if you don't think about it too closely, this kind of makes sense. We're like, well, I just got 6 successes and only 1 failure after 7 goes. So probably, probably there's a reasonably good chance that I'll do things right, that I'm successful on a given toss. I mean, I got 6 out of 7. That's pretty good. It's probably like a biased thing. So, of course, that use of the word probably is actually not a probability use, unfortunately. This actually, so if I say this as a question, is the probability that theta is, what's the probability that theta, what's the probability that theta is at least a half? Is this even like a question we can ask? And the answer is, this doesn't really make sense. And the reason is that, theta isn't a random variable. It's not something that's being kind of picked. It's just the probability that it's there in the population. Theta is what it is. It's either greater than a half or not greater than a half. And it's not a matter of sampling and checking actually the value of theta. And the value of theta is just what it is. It's a number. It's not a random variable, right? Theta is a number, not a random variable. Well, I guess strictly speaking, it's a constant random variable, which means that I guess this makes sense. The probability is either 0 or 1 if it is or if it isn't, right? But in any case, the point is that theta is not a random variable. It's just a number. On the other hand, what we do, the whole point of this is we want to estimate these parameters theta. And of course, the process is that instead of thinking about theta as a random variable, we pick some other random variables. So we don't do this. Instead, we find other random variables, other variables that are actually random. Call it, let's say, theta hat, these so-called estimators, for example, whose distributions are related to the value of theta, or whose distributions carry information about the value of theta. For example, the variable might be x hat. So x hat is a random variable whose expected value is the value of theta. And so we might imagine that x bar, or we know that x bar tends to be close to the value of theta. So in other words, theta hat equals x bar is an estimator for theta. And so we kind of make then the estimate, the point estimate, that in our particular case we got a measured value of 6/7 for our sample mean, and that says that this is our estimate for this parameter theta. All right. So now again, I mean, this doesn't necessarily mean that that is actually close to theta. I mean, theta is what it is. It's an unknown thing. It either is close to 6/7 or it's not. It's not a matter of probability. But what is the kind of probability statement? The probability statement is that, we can talk about the probability that this random variable is close to the actual value of theta. And so we can say, like, if we make a lot of measurements, then we expect this to be close to, these measurements we get to be close to this, etc. But now today, we're going to talk a bit about a different way that the game could be played, at least for a little while. And that is the so-called Bayesian approach. So in the Bayesian approach, we start with a different kind of information. So if you think about what happened in our case of this say Twain-Coase or Bernoulli trial, we didn't have any prior or a priori kind of information about what the possible values of our probability might be, of our parameter theta might be. We didn't have reason to believe that it was probably going to be close to 50-50. We didn't have reason to believe that it was going to be either close to 1 or close to 0. We really didn't have any information that we could use about kind of like how likely different things were. And of course that made some sense because we were thinking of this as like a fixed population out there. We weren't thinking of it as like some possible population in the kind of infinities of different potential populations that are out there, that we had somehow selected some random member of the population of populations or something like that. But this time we're going to essentially assume just that. So let's look at the following kind of example before I say what's generally happening. So let's suppose we have a box of potentially biased coins. So, and moreover, we know something about the distribution of these biases. We know that it's just as likely that I'll get a coin with a 30% heads as I will with an 80% heads, as I will with a 50% heads. In other words, I'm going to assume that the different parameters, these thetas, are uniformly distributed in the box of coins. Okay, so the parameter theta is actually going to be a random variable. Maybe I should give it like a, so I shouldn't call it theta. Let me say, yeah, the parameter theta is going to be replaced by a random variable, which maybe I'll call capital theta. And the idea is, how is capital theta kind of chosen in practice in this experiment? Well, we simply choose a coin from this box of coins, and capital theta is the random variable which tells me what kind of coin I just picked up. Okay, so now the situation is now a bit different. So instead of before, now it actually makes sense just to ask things like, what's the probability that this random variable is at least a half? This is the probability of picking a biased coin with a bias of at least a half. If it's uniformly distributed, that's going to be a half for us, for etc. Okay, but moreover, if we so really let's just assume that now what we're really saying is that theta is a random variable, and let's say its density function is some g of a particular value, little theta. Okay. So, for example, the probability that capital theta is in some interval AB should be the integral from A to B of the density function d theta. Okay, so that's what we mean. Okay, so now let's also observe that we can more or less now pull up a joint density function in some sense. So that is to say, we know in our particular case what's the probability of measuring a certain value, 0 or 1. Let's say, actually, maybe I shouldn't write it like that. See, this is a little bit awkward. But what's the probability that I measure a certain value for x? Well, how about, let's say I can say probability that x equals 1 given theta. Right. So, so I know what is this. This is actually just theta. It's theta. Excuse me. Right. That's it. Okay. And, so I have a kind of a joint density function, if you will, probability of, a conditional probability distribution, or probability function, probability of x given theta. And this is just theta. But now I also have a probability density function for theta, which for us is 1 if theta is in 0, 1. It's the uniform distribution, and 0 otherwise. Okay. Now, from these two things, you can combine that information and come up with a kind of joint density, or this is like a probability / density function, I guess, because I have one discrete coordinate and one continuous coordinate. So let me just, what letter should I give that? I'll just call it F, even though we'll just remember that that x has two values and theta has infinitely many values. But so it's f of x, comma theta. It's kind of a joint function, joint distribution density function. And this is going to be the probability of x given theta times the density function for theta. Okay, so this is kind of a post hoc reconstruction way of thinking about what this joint density function is. I wasn't given this joint density function. Rather, I know what this thing is, and I'm interpreting it as a conditional probability so as to come up with this kind of a notion. But then from that, I can come up with a conditional probability going the other way. I can say, what's the probability, or the density function for theta, given a particular measurement for x. And so what I can kind of evaluate, the way I can think about that is just the same kind of construction in reverse, the Bayes formula. So what is it? It should be the joint density divided by the marginal density for x. So this is the integral over the thetas, f of x theta d theta for that particular value of x. Okay. So like, for example, let's do the coin example. So if we, let's say if we toss the coin once and get heads, which, well, let's just interpret that as 1. Then what do we know for, what do we know about theta? Right. So I guess I should more clearly describe exactly what the plot is here, right? So we start out with some a priori information about how theta is distributed, but then we run an experiment. Okay. Now, after we run an experiment to measure our sample numbers, then the idea is that our distribution, our knowledge of the distribution of theta changes. We have new information, and that changes our distribution in what way? Well, after we do our experiment, we can talk about the conditional probability of theta having certain values, or the probability density function for theta, conditioned on having made our measurements. And that's what I'm trying to explain here. So after we make a measurement for our variable, then we can get a new density function for our parameter, which is this conditional density function. Okay. So as an example, we again have this box of coins, equally likely to get any particular coin. We grab one, we toss it, we get heads. Now that particular coin, we can think about its probability, its theta parameter, as some random variable, but it's less unknown than it was before. So and we can describe that with the conditional probability. So we can say in this particular case, let me just remind ourselves how it works in this case. So we have the probability for x given theta. So this is theta if x equals 1. So the probability is a theta of getting a 1, and it's a 1 minus theta if x is equal to 0. A probability of theta giving a 1, probability of 1 minus theta of getting a 0. Okay. This is what I was calling P a moment ago. I guess I'm a little indecisive about what to call it. Okay. We also have our density function for theta. So theta is uniformly distributed, so it's a 1 if theta is in 0, 1, and 0 otherwise. We have our joint density, which is this thing that we're artificially kind of putting together, which is given like so. So for us, this is, so what is it? It's theta if x equals 1, and if theta is in 0, 1, it's 1 minus theta if x equals 0, and theta is in 0, 1, and it's 0 otherwise. Okay. And so now we can talk about our conditional probability. So for example, what do we know about our distribution if we flip our coin and measure a 1? We know, so we're going to write this as g of theta given that x is equal to 1. So how do we work out this conditional probability of our conditional density function for theta? So as we just described a moment ago, this is, so the formula for this is f of the joint density function divided by the marginal density. Oh, actually, of course, this is the value for x, so I'm really evaluating this at 1. Okay. F of 1 theta, that's f of 1 given theta times the probability of theta divided by the marginal density, which is the integral over theta of going from 0 to 1 of this thing on the top. Okay, and let's work that out. So f of the probability of getting a 1 given theta times the probability of having a given theta. This g of theta is 1. This thing, first thing is just a theta. I get a theta in the top. And then in the bottom, I have an integral of really the top, which is theta, d theta. So that's 2 theta, right? So it's theta over the integral of theta d theta, that's 1/2 theta squared, evaluated from 0 to 1 is 1/2. So I get 2 theta. And of course, theta is in 0, 1. And so what do we find out? We find that, so one way to think of this is initially we had a uniform density for theta described by this function g. And it's uniformly distributed from 0 to 1. After getting a 1, so this is the a posteriori distribution. We are measuring g of theta given x equals 1, and that density function from 0 to 1 does this instead. So, so it looks like the function, 2x, if you will, or 2 theta in this case. So this is 2 theta, which makes sense. Once you flip a 1, there's a 0 chance that you have a 0 and a much higher chance that you have a 1. Okay. So the procedure is we start with some form of a probability density function, f of x, f of x given theta, for our population, with parameter theta. And we suppose that we have some knowledge, some prior knowledge of possible values for theta, i.e., theta is actually some unknown value of a random variable, capital Theta, whose distribution we quote-unquote know. That is, you have some initial guess, at least, for what the distribution is supposed to look like for capital Theta. So maybe it's the parameter you're assuming is uniformly distributed out of some possible large population of possible things you could be looking at, etc. Okay, some prior knowledge of theta. So then we sample and use our measurements to produce a new probability distribution via conditional probability for our parameter theta. Okay. We replace our original random variable with some new random variable, which is somehow the original one conditioned on having measured, x equals x. So that is to say that if this had some density function g of theta, then this one is going to have the density function for the conditioned variable, conditioned on that particular value for x. Okay, and this new probability distribution for theta is the a posteriori distribution. It's the distribution that we can make after having some new knowledge of our parameter based on having measured the sample in the way that we just did. Okay. Let's just finally wrap up by considering the Bernoulli example, so the coin flip example. so what happens if we keep flipping and get some new x1 through xn, a bunch of zeros and ones? Really all we care about is like maybe k equals the number of successes. N is the number of trials. Of course, that's really what we're getting in your repeat that experiment is a binomial random variable. Then the distribution for theta, which starting at uniform, becomes a beta distribution. Okay, so you can see this just a bit. So remember the beta distribution. So to say that g of theta has a beta distribution is to say that it has the form gamma alpha plus beta over gamma of alpha, gamma of beta, x to the alpha minus 1, 1 minus x to the beta minus 1. And of course, x is just from 0 to 1 for the beta distribution. And this, of course, is some g which is really depending on a couple of unknown parameters, a couple of parameters alpha and beta. So note that if alpha equals 1 equals beta, then both of these exponents are just 0, and this is just a constant function. And we get the uniform distribution on 0, 1. If alpha is equal to, so this is, for example, this is our prior distribution. If alpha is equal to 2 and beta is equal to 1, you get that it's g of theta is 2 theta on 0, 1. Right. So 2 minus 1 is, so this is just alpha to the 1, and 1 minus alpha to the 0. And so we get this familiar friend. And this is our posteriori distribution. And more generally, you can show that if we get k successes and n minus k failures, then the a posteriori distribution is beta, with alpha being 1 plus the number of successes, and beta being 1 plus the number of failures.